In these two examples, we're going to look at finding gradient fields. So a gradient field is really just the set of vectors at each point in space. So we're just going to find the gradient. Now remember, in our definition of the gradient, we need the partial of this function g with respect to x, y, and z. So partial of g with respect to x is going to give us negative 2x over x squared plus y squared. This is a constant. Taking the derivative of this with respect to x, remember the derivative of a logarithm is the derivative of the argument over the argument. So the derivative of that argument would be x squared. The derivative of g with respect to y would be very similar, but we'll end up with negative 2y over x squared plus y squared. And the derivative of g with respect to z would just be e to the z. So my gradient field of g would be negative 2x over x squared plus y squared I plus, actually I'll write minus, so minus 2y over x squared plus y squared j plus e to the z k. So at any x, y, z point on this g, our gradient, we could plug x, y, and z into this, and we would get a gradient vector. And all of these vectors would be pointing, which way does the gradient vector point? In the direction of steepest ascent or maximum increase. So they would all point where things are moving the fastest or changing the fastest. And this is really just a difficult visualization for us to plot a gradient field this large, but that's how we would find it. So let's get one in two variables, which may make a little bit more sense or be more helpful to us. Consider we're given the function phi of xy equals x squared plus y squared. We're asked to sketch the gradient field. First of all, what is the shape of this function? It's a circular or elliptical paraboloid. Finding the gradient, that gradient field for phi, is going to be partial with respect to x, 2x, partial with respect to y, 2y, or 2xi, 2yj, whichever notation you prefer. Obviously, this is a little shorter. I know your textbook, this is what you see in my math lab, so that's why I always kind of stick with that. So let's think about some paths that we can look at where we should plot some vectors. One thing we could always do is be looking along these axes, so at some points along the axes. And since this is a circle, right, or an elliptical paraboloid, it's actually a circular paraboloid. This is our surface that we are considering, or we're drawing the gradient field for. I'm going to choose points around that circle. I'm going to draw a level curve here and try to make this look as nice as I can of a circle radius 1. And we'll look at these 4 points on the circle, which are 1, 0, 0, 1, negative 1, 0, and 0, negative 1. And what are the vectors that those create? Well, we've got 2, 0. Oh, I need to use vector notation. My angle brackets. 2, 0, 0, 2, negative 2, 0, 0, negative 2. So I'm going to draw each of those. This one is 2 units long. This guy is 2 units going up, 2 units to the left, and 2 units to the right. And essentially every vector I draw along that circle is going to give me that vector of that length. So I'm going to go through, I'm going to make another circle. This one passes through all the points, 1, 1. So it actually has a radius of √2. Right, let's look at graphing some of these. So those points, I'm going to pick 1, 1, negative 1, 1, 1, negative 1, and negative 1, negative 1. So those are these 4 points here. So they're out a little bit further, and what we're going to notice, all these blue vectors that we drew, those were of magnitude 2. These are all going to have a magnitude √2. So this will give me a vector 2, 2. We have negative 2, 2, 2, negative 2, and negative 2, negative 2. We get these vectors here that are, again, slightly longer, right? So this is just, we could do this all day. I know this gets rather repetitive, so I'm going to bring in a picture, but this is the idea of creating that vector field. And when we consider our shape, it makes sense that these are the directions straight off of these level curved circles. That's of the direction of maximum increase. So this is what the vector field for this circle would look like. I'm sorry, elliptical paraboloid, circular paraboloid. Look like if we continued drawing these vectors forever. I just feel like it's easier to pull in a picture and kind of show you. As those level curves, as they move out, you'll notice that the vectors become longer. Again, remembering that they're always pointing in the direction of maximum increase, this makes sense that they're all pointing directly out off of those circles. One thing to keep in mind is that these gradient vectors, these are equal to the directional derivatives at any point on this surface. At this point, anyhow, I hope you feel a little bit better about visualizing a vector field, because in a second, we're going to be calculating line integrals over vector fields. And it's helpful to know what you're dealing with when you are calculating something across it. Again, if we were in class, we would be doing more practice with Maple, but I encourage you to just Google vector field plotter, especially maybe as you're working on some of these problems in the homework, to have a good visualization of what you're looking at. And if you need help finding something or a resource to create that picture for you, since we are in this strange virtual environment, just send me an email. I would love to help.